Partial differentiation, introductory situation 2. Consider z is equal to fxy, where x and y are independent variables. So z is some function of x and y. We can plot this situation on a 3D graph, perhaps using a 3D plotter. I found one online to get a picture of the situation. So, for example, 3D plotter has produced a graph like this. The function I used here was that z was equal to negative x squared plus y squared plus 4. We can look at this situation, how it's changing along the x-axis. We can look at how the curve is changing just in the x direction by evaluating dz dx, how z is changing when x changes, keeping y constant. Now expanding this bracket gives me z is equal to negative x squared, take away y squared, plus 4, and therefore dz dx is just negative 2x. Remember, y is a constant here. We could also look in the y direction, keeping x constant. So we can look at how the curve is changing just in the y direction by evaluating dz dy. Since z is negative x squared, take y squared plus 4, dz dy is equal to negative 2y. Both dz dx and dz dy are 0 at this point just here, where x and y are both 0. And because it's negative 2x and negative 2y, as we move away from that point, we can see the gradient is sloping us downwards. And that's why we end up with a maximum. So using this plotter, we can move around this curve, and you can see that it is a maximum in every direction. We can spin this around, we can look at it from on top, it looks like the top of a hill, and we can go and look at it from the bottom. So we can see that it is a maximum. As a second example, this is a plot of z is x squared plus y squared take away 4. We do dz dx for this one, it's 2x, and dz dy is 2y. So along the z-axis, where x and y are both 0, we get this minimum point. dz dx is 2x, dz dy is 2y. So as we move away, if we move away in the x direction, then we're going to have a gradient sloping upwards. And if we move away in the y direction, we'll have a gradient sloping upwards. And therefore this gives us a minimum. So here's a look at this one. We can move around and look at it from on top, and we can then look at it from underneath, and we can see it is indeed a minimum in every direction. As a third example here, let's look at this one. This is z is x squared minus y squared, and this is known as a saddle point. We're looking at it from a slightly different direction here. And what you can see, certainly you'll see it when we go to the animation, is that it's a maximum in one direction and a minimum in the other direction, just like a saddle. Here we get that dz dx is 2x and dz dy is negative 2y. So if we go away from the saddle point here, where x and y are both 0, and therefore dz dx is 0 and dz dy is 0 there, if we move away in the x direction, the gradient is positive, but if we move away in the y direction, the gradient is negative. So let's look around this saddle point. You can see as we move around that along the x-axis we do have a minimum, and along the y-axis, we do have a maximum. So let's look at this much more complicated surface. This one is z is sine x plus cos y. For this one, dz dx would be cos x. Remember, the y is a constant, so cos y is just a constant, and therefore will evaluate to 0 when differentiating with respect to x. Similarly, dz dy would be negative sine y. And of course, we could use these to consider where the minima and maximum are as we move along the x direction and as we look along the y direction. So we can see as we move around that this does produce a more complex surface, although a completely predictable one from the function.